The morning of January 5, 1943. The waters off Guadalcanal shimmer under a tropical sun that's already turned the steel deck of the cruiser USS Helena into a griddle hot enough to fry eggs. Lieutenant Commander Francis "Red" Cochrane stands at his station commanding the aft 5-inch battery, squinting through the glare as his radar operator calls out ranges and bearings with mechanical precision. Somewhere in that brilliant blue sky, 4 Japanese Aichi-D, 3A dive bombers, the Naval, are completing their attack run, one having just scored a hit on the New Zealand cruiser Achilles. The Navals are pulling away now, climbing for altitude, their pilots confident they've accomplished their mission and survived another day over the killing ground that American sailors have taken to calling Iron Bottom Sound. Cochrane doesn't need to give elaborate orders. His gun crews have trained for this exact scenario dozens of times. What makes this moment different? What makes this morning historically significant, though none of the men firing these guns yet understand it, is what's loaded in their breech. Not the standard Mark 18 mechanical time fuse that requires a petty officer to manually set the detonation time before each round is loaded. Not the contact fuse that only explodes if it physically strikes something. These shells carry something new, something that's been transported across the Pacific under armed guard, with security protocols normally reserved for gold bullion, something the Japanese have never encountered before. The first salvo screams into the sky at 2,800 feet per second. The second salvo follows 3 seconds later, then the third. Cochrane watches through his binoculars as the third salvo creates a pattern of black smoke puffs in the air near the retreating dive bomber. One of those puffs appears directly adjacent to the Naval's fuselage, not hitting it, but close enough. The aircraft shudders in mid-air. Pieces of metal tear away from its wings. The bomber's nose drops, and it begins its final, uncontrolled descent into the Solomon Sea, trailing smoke like a funeral shroud. 3 salvos, 9 shells. 1 kill without a single direct hit. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The gun crew erupts in celebration, but Cochrane is already calculating. His men have just participated in the first combat kill using a weapon system that will, before this war ends, fundamentally alter the mathematics of naval warfare. They've proven that a technology the British considered impossible for artillery shells, a technology so secret that even the existence of these particular rounds aboard Helena was known only to a handful of officers, actually works under combat conditions. More importantly, they've demonstrated that American 5-inch naval guns, previously effective but limited in their anti-aircraft role, have just become the most lethal ship defense weapons in human history. What Cochrane doesn't know, what nobody in the American military fully comprehends yet, is that this morning's kill represents the opening shot in a technological race that the Japanese have already lost before they even know. They're competing. The VT Fuse's revolutionary miniaturized radar system had just proven its worth in combat, forever changing the mathematics of naval warfare. The Japanese pilot who just died never understood what hit him. Neither do his commanders back at Rabaul when they receive the after-action report. Neither will Japanese naval intelligence for most of the next 2 years. They will notice that American anti-aircraft fire has become uncannily accurate. They will observe that their aircraft are being destroyed at ranges and in circumstances that should produce only near misses. They will develop theories about improved American gunnery training, about new fire control radars, about anything except the truth that the Americans have put working radar sets inside artillery shells and turned every near miss into a kill. This gap in understanding, this fundamental failure to recognize that physics and engineering have shifted the battlefield's rules, will cost the Imperial Japanese Navy thousands of aircraft and tens of thousands of trained pilots. It will contribute directly to one of the war's most desperate tactical innovations, the Kamikaze Special Attack Corps, born partly from the recognition that conventional dive bombing and torpedo runs have become suicide missions with success rates approaching 0. And it will demonstrate, with brutal mathematical clarity, what happens when one side in a technological war makes an impossible thing possible while their opponent doesn't even believe the impossible exists. The story of the VT fuse, the innocuous designation chosen specifically to obscure its true nature, begins not in 1943 but years earlier, in the recognition of a problem that seemed to have no solution. Naval anti-aircraft gunnery in the late 1930s and early 1940s existed in a state of almost complete futility. The mathematics were punishing. A fast-moving aircraft presented a target roughly 30 feet long and perhaps 40 feet across its wingspan. At typical engagement ranges of 3,000 to 5,000 yards, that aircraft subtended an angle of perhaps half a degree. The shell had to arrive at precisely the correct point in three-dimensional space within a window of perhaps 0.2 of a second, the time it took for that aircraft to move through the lethal radius of the explosion. Traditional contact fuses were useless. The probability of a direct hit on a maneuvering aircraft at range approached zero. Statistical analyses from the 1930s suggested that even with perfect aiming, a ship might need to fire several thousand rounds, achieve a single direct hit against a crossing target. Mechanical time fuses offered improvement, but they introduced their own cascade of problems that would prove nearly insurmountable under combat conditions. The time fuse, in theory, worked simply enough. Before loading, a gunner would set a small clockwork mechanism to a specific number of seconds. When fired, the acceleration of launch would start the timer. After the predetermined interval, the fuse would trigger detonation. The gunner, working with rangefinder data and predictions about the target aircraft's course and speed, would calculate how many seconds the shell needed to travel before reaching the optimal detonation point, set the fuse accordingly, and hope everything worked as planned. In practice, this system failed at almost every stage. The calculation itself required solving complex trigonometry in real time while under fire. The aircraft's altitude, speed, and angle of approach all affected the correct fuse setting. A bomber flying straight and level at 10,000 feet required one setting. The same bomber diving at 300 miles per hour required a completely different setting that changed second by second. The clockwork mechanisms themselves, while precise when stationary, often failed to function reliably after experiencing the violent shock of firing 20,000 times, the force of gravity, compressing every spring and gear in the mechanism over a distance of inches. Even when everything worked perfectly, the system suffered from an inherent time lag that bordered on the catastrophic. The gun crew would observe the aircraft, calculate the required time to target, set the fuse, load the shell, aim, and fire. That entire sequence took perhaps 15 to 20 seconds for a well-trained crew, but in those 15 to 20 seconds, the aircraft had moved. A bomber approaching at 200 miles per hour covered nearly a mile in 20 seconds. The carefully calculated fuse, setting, perfect when determined, was obsolete before the shell even left the barrel. Gun directors' mechanical computers that attempted to predict a target's future position helped somewhat. These elaborate devices, incorporating gyroscopes and early analog calculating mechanisms, could track a target's motion and extrapolate where it would be several seconds in the future. But they couldn't account for evasive maneuvers. They couldn't compensate for windage variations at different altitudes. They couldn't adjust if their initial tracking data was even slightly inaccurate. And they certainly couldn't make the fuse setting problem disappear. They only made the calculations faster, not perfect. The result was that naval anti-aircraft fire in the early years of World War II amounted to expensive noise. Ships would pour hundreds, sometimes thousands of rounds into the sky during an attack. The shells would create impressive patterns of black smoke puffs, barrage fire designed more to make pilots nervous than to actually hit anything. Occasionally, a bomber would fly directly into one of those detonations through sheer bad luck. More often, the attacking aircraft would complete their bombing or torpedo runs and fly away unscathed while the ships below burned through their ammunition magazines, accomplishing nothing. Statistics from 1941 and early 1942 paint a stark picture. The Royal Navy, analysing anti-aircraft performance during the early stages of the war, determined that their ships required an average of 2,500 rounds fired to achieve one aircraft kill. The United States Navy's numbers were similar. Japanese naval forces reported comparable inefficiency in their own defensive gunnery. Every major navy had recognized the problem. Every major navy understood that aircraft were becoming the primary threat to surface vessels. But nobody had solved it, and most naval architects believed it couldn't be solved with existing technology. The British, characteristically, were first to seriously pursue an alternative. In 1939, before the war even began, researchers at the Telecommunications Research Establishment began exploring the concept of a proximity fuse, a device that would somehow detect when a shell had approached close enough to a target to make detonation worthwhile. The conceptual appeal was obvious. Remove the need for precise timing, remove the need for prediction, simply put intelligence into the shell itself, and let the shell decide when to explode. Several approaches seemed theoretically possible. An optical system that measured reflected light could detect an aircraft's presence. An acoustic system listening for engine noise might trigger detonation. A magnetic field detector could sense the metal mass of an aircraft passing nearby. Radio waves bounced off the target and measured for their return time offered another potential solution. Each approach had advocates. Each had apparent advantages. Each also had what appeared to be completely insurmountable engineering challenges. The optical approach seemed promising initially. Shine a light beam from the shell. Measure how much light reflects back. When reflection exceeds a threshold, detonate. Simple in concept, impossible in practice. The device would need to distinguish between reflections from clouds, from the sun, from the ocean surface, and from an actual aircraft. It would need to remain calibrated despite spinning at 25,000 revolutions per minute. It would need to function after experiencing forces that would pulverize any conventional light sensor, and it would need to do all of this using 1930s electronics that typically filled an entire laboratory bench. Acoustic detection faced similar issues magnified by the physics of supersonic travel. The shell itself created so much noise moving through the air at Mach 2.3 that any microphone mounted on it would be immediately overwhelmed by the sound of the shell's own passage. Magnetic detection required fields strong enough to sense an aircraft at dozens of yards distance, but those same fields would wreak havoc with the fuse's own circuitry. Every approach that seemed feasible on paper dissolved into impossibility when engineers attempted to design actual hardware. The radio approach using reflected radio waves to measure distance had its own catalogue of problems, but it also had one critical advantage. Radio proximity sensing was already proven technology. Radar worked. British chain home stations were tracking incoming Luftwaffe bombers from distances of over 100 miles. The physics were understood. The basic engineering was known. The challenge wasn't whether radio ranging could detect an aircraft. The challenge was whether anyone could miniaturize a complete radar set to fit inside an artillery shell's nose cone and make it survive being shot out of a gun. British researchers, working through 1940 and early 1941, concluded it couldn't be done, not with available technology, not during the current war. The components were simply too large, too fragile, too power-hungry. A standard radar transmitter required vacuum tubes the size of light bulbs. Those tubes needed substantial power supplies. The circuits required careful shielding and precise calibration. Pack all of that into a space smaller than a pint milk bottle, subject it to 20,000 gravities of acceleration, spin it at 25,000 RPM, and expect it to work afterward? Impossible. The British reached this conclusion reluctantly, documented their research carefully, and moved on to exploring other defensive measures. This was the state of proximity fuse research when the Tizard mission arrived in the United States in September of 1940. Sir Henry Tizard and his scientific delegation came bearing gifts the full details of British radar development, including the cavity magnetron that would revolutionize microwave radar. Buried in their technical documents were also the British findings on proximity fuzzes, including the detailed explanation of why artillery shell applications couldn't work with existing components. American researchers read those documents and reached a different conclusion. Not that the British were wrong about the technical challenges. Those were real and daunting. But where the British had seen insurmountable obstacles, American scientists saw engineering problems that might yield to sufficiently determined effort and sufficient resources. The U.S. Navy, acutely aware of its vulnerability to Japanese air attack after the carriers had demonstrated their dominance at Taranto, designated proximity fuse development as one of its highest priorities. The National Defense Research Committee assigned the project to Section T, housed at the Applied Physics Laboratory of Johns Hopkins University. Dr. Merle A. Tuve, a 40-year-old physicist with expertise in radio technology and a reputation for turning theoretical concepts into working hardware, took charge. Tuve assembled a team that would eventually grow to 700 people. But in those early months of 1941, it was a handful of physicists, electrical engineers, and ordnance specialists working with a mandate that bordered on science fiction. Build a complete radar system that fits in a 5-inch shell, survives being fired from a naval gun, and actually functions reliably enough for combat use. The team began by listing everything that had to work. The device needed a radio transmitter powerful enough to send a signal that would reflect measurably off an aircraft at useful range, probably 50 to 100 yards. It needed a receiver sensitive enough to detect that reflection amid the electromagnetic noise of its own transmitted signal. It needed a power supply that could deliver adequate current for the fraction of a second required. It needed a battery that would remain stable in temperatures from 100 degrees above zero to 50 below, that would survive storage for months, and that would instantly become operational when needed. It needed all of this packaged so compactly that 7 pounds of high explosive could still fit in the shell casing alongside the electronics. And critically, every component had to survive the launch. When a 5-inch Mark 12 gun fired, the shell experienced acceleration from 0 to 2,800 feet per second over a barrel length of 25 feet. That meant an average acceleration of over 3,000 feet per second squared, or just under 100 gravities. But the acceleration wasn't average. It peaked much higher during the instant of maximum pressure. Components needed to withstand forces exceeding 20,000 times their normal weight. A vacuum tube weighing an ounce effectively weighed 25 pounds for the milliseconds of peak acceleration. Every solder joint, every wire, every fragile glass envelope had to remain intact under stresses that would turn conventional electronics into fragments. The rifling added another layer of complexity. The gun's barrel featured spiral grooves that imparted spin to stabilize the shell in flight. That spin reached 25,000 revolutions per minute, or over 400 rotations per second. Every component had to function while experiencing centrifugal forces that would fling unsecured parts outward with tremendous force. Every circuit had to remain electrically stable despite the mechanical stresses that spinning would create. The vacuum tube problem emerged as the most critical challenge early in development. Every radio circuit of that era depended on vacuum tubes, glass envelopes containing a heated filament, metal plates, and control grids suspended in vacuum. Electricity heated the filament to high temperature, causing it to emit electrons. Those electrons flowed through the vacuum to the plate, and the control grid modulated that flow, enabling amplification and oscillation, the basic functions needed for radio transmission and reception. Ordinary vacuum tubes were extraordinarily fragile. Drop a standard radio tube from table height onto a hard floor, and you'd likely shatter the glass envelope or break one of the internal elements. Subject that same tube to 20,000 gravities, and you wouldn't have a broken tube. You'd have glass powder and twisted wire. Standard tubes had to be completely reimagined from first principles. The solution emerged from an unexpected source. The Western Electric Company and Raytheon manufactured miniature vacuum tubes for hearing aids. These tubes, designed to be compact and relatively rugged for portable use, used thicker glass, heavier internal supports, and more robust construction than standard radio tubes. They weren't nearly strong enough for artillery use, but they represented a starting point. Section T, engineers worked with the tube manufacturers to develop specialized designs, tubes with glass envelopes thick enough to resist shattering, with internal elements supported by multiple heavy-duty supports. with every component overbuilt to withstand forces far beyond any civilian application. Even these ruggedized tubes failed spectacularly in initial tests. Engineers would carefully install a prototype fuse in a test shell, fire it from a gun, and recover a fuse filled with glass fragments and broken components. They would modify the design, thicker supports here, different glass there, and try again. More failures, more modifications. Gradually, through hundreds of test firings and continuous iteration, they developed tubes that could survive. Not perfectly, even the final production tubes had failure rates that would have been unacceptable in any civilian application, but well enough for military use. The radio circuit itself had to be fundamentally different from standard radar. A conventional radar used separate transmitter and receiver circuits with complex timing to alternate between transmission and reception. No room for that in a 5-inch shell. Section T's engineers developed a design where a single tube functioned as both transmitter and receiver, simultaneously an autodyne circuit, where the oscillating tube continuously broadcast its signal while simultaneously detect any changes in that oscillation caused by reflected energy. The principle exploited the Doppler effect. As the shell approached an aircraft, the radio waves reflected from that aircraft would return frequency shifted proportional to the closing velocity. The transmitted frequency and the received frequency would beat against each other, producing a low-frequency signal that changed as the range changed. Amplify that low-frequency beat signal, filter it to distinguish it from noise, and use it to trigger detonation when it reached values corresponding to optimal range. In theory, this worked elegantly. In practice, it required circuits of extraordinary stability and sensitivity, circuits that had to function inside a metal shell, spinning at 400 revolutions per second, surrounded by high explosive, operating for perhaps 10 to 15 seconds from launch until either detonation or impact. The engineering tolerances were microscopic. The margin for error was non-existent. The power supply represented another fundamental problem. The vacuum tubes needed several tens of volts to operate. The circuits required stable power despite the mechanical chaos of flight. Conventional batteries of sufficient capacity were too large to fit in the available space. Custom battery designs had to be developed, power sources compact enough to fit yet capable of delivering adequate current for the seconds of operation required. Early designs used dry cell batteries similar to those in flashlights, but scaled down and ruggedly constructed. These worked but suffered from limited shelf life. Batteries would slowly lose their charge over months of storage, and there was no way to determine if a particular fuse's battery remained viable without testing it. The Navy found this unacceptable. They needed fuses that could be stored for extended periods and remain reliably functional. Later designs incorporated a wet battery that was activated by the centrifugal force of firing. The battery's electrolyte remained separated from the electrodes until the shell's spin forced it into contact, instantly bringing the battery to full power. This solved the storage problem beautifully. Fuses could sit in magazines for months and activate instantly when needed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By early 1942, Section T had working prototypes that survived firing and detected targets reliably in laboratory conditions. The next challenge was proving combat reliability. The Navy arranged live-fire tests at their proving ground in Dahlgren, Virginia, and at several other locations. The targets were drone aircraft, remote-controlled planes that could be maneuvered to simulate attack runs, while test gunners attempted to shoot them down. Initial tests were disappointing. Roughly half the fuses failed to detonate at all. Some detonated prematurely. Others passed within lethal range of the target without triggering. The engineers went back to their benches and refined the designs. More test firings, gradual improvement. By summer of 1942, reliability had climbed to acceptable levels, not perfect, but good enough that the Navy ordered the first production batch. In August 1942, the newly commissioned light cruiser USS Cleveland conducted what was supposed to be a 2-day evaluation of VT fuses in the Chesapeake Bay. 3 remote-controlled drone aircraft would fly. predetermined patterns, while Cleveland's gunners engaged them with proximity-fused ammunition. The test was scheduled to evaluate reliability, optimal firing procedures, and any unexpected issues that might emerge before committing to full-scale production. The test ended on the first day. Cleveland's gunners brought down all 3 drones using just 4 salvos total. The drone operators attempted evasive maneuvers. Didn't matter. The VT-fused shells compensated automatically for any movement. Every shell that came close enough to matter detonated at optimal range, sending a cone of steel fragments through the drone's flight path. The Navy's test coordinator watched the 3rd drone disintegrate and immediately cancelled the remainder of the testing schedule. There was nothing left to test. The system worked beyond all expectations. Production accelerated rapidly. Multiple contractors received orders: Crosley Corporation, RCA, Eastman Kodak, General Electric, McQuay Norris, and several others. By the end of 1942, factories were assembling 500 fuses daily. The Navy wanted thousands. They wanted them immediately. And they wanted absolute secrecy about what these fuses did and how they worked. Security around the VT fuse program reached levels normally reserved for code-breaking operations and nuclear weapons research. Workers in the manufacturing plants never saw complete fuses. They assembled components without knowing what those components did or how they fit into the final device. Different contractors manufactured different subassemblies. Final assembly happened at secure facilities, where finished fuses were immediately packaged and shipped under armed guard. The secrecy had desperate practical importance. If a single intact dud VT fuse fell into enemy hands, Japanese or German engineers could potentially reverse engineer it. They could develop their own proximity fuses. Or worse, they could develop electronic countermeasures. Radar jamming was already understood technology. If the enemy realized that American shells contained miniature radars, they might develop transmitters to flood those frequencies with noise, rendering the fuses useless or causing premature detonation. This security concern created a strict operational limitation. VT fuses could only be used over water. If a shell malfunctioned and failed to detonate, it would sink harmlessly into the ocean where the enemy couldn't recover it. Land use was absolutely forbidden, no matter how tactically advantageous it might be. This restriction would hold through most of 1943 and into 1944, preventing the Army from using proximity fuses in Europe, even as the Navy was revolutionizing Pacific naval warfare. In October 1942, Commander William Deke Parsons, a naval ordnance officer deeply involved in the VT fuse project, personally escorted the first combat shipment to Pearl Harbor. 5,000 rounds fitted with Mark 32 VT fuses, packed in specially marked containers with security protocols emphasizing that these rounds were never to be fired where a dud might fall on land. From Pearl Harbor, the rounds traveled to Noumea, New Caledonia, where Admiral William Bull Halsey's South Pacific Force prepared for operations around Guadalcanal. Halsey's staff selected 3 ships for initial distribution: the carriers USS Enterprise and USS Saratoga, and the light cruiser USS Helena. All 3 received approximately 500 VT-fused rounds, plus extensive training on their proper use. The training emphasized security. Gun crews were told these were a new type of special anti-aircraft shell. They were told the shells would explode near targets without direct hits. They were not told how this worked, and they were explicitly ordered never to discuss the shell's performance with anyone outside their immediate command. Helena, freshly returned to the Pacific after repairs following torpedo damage at Pearl Harbor, had already established herself as one of the most formidable fighting ships in the fleet. Her 15 6-inch guns could throw devastating weight of fire in surface engagements. Her 8 5-inch dual-purpose guns provided both anti-aircraft defense and surface fire support capability. She carried the latest radar fire control systems, and she was commanded and crewed by men who'd already proven themselves in some of the war's most intense battles. Through late 1942 and early 1943, Helena operated continuously in the increasingly violent struggle for Guadalcanal and the surrounding waters. She participated in the Battle of Cape Esperance on the night of October 11th to 12th, 1942, where her rapid-fire 6-inch battery helped sink the heavy cruiser Furutaka and the destroyer Fubuki. She fought again in the furious night action of November 13th, the first night of the naval Battle of Guadalcanal, where American cruisers and destroyers clashed with a Japanese bombardment force built around the fast battleships Hiei and Kirishima. Helena's guns helped cripple Hiei. The battleship would be finished off by aircraft the following day. But through all of these engagements, Helena's gun crews used conventional ammunition. The VT-fused rounds remained carefully segregated in the magazines, waiting for the right moment an air attack where they could be employed without risk of duds falling on land, where their effectiveness could be evaluated under actual combat conditions, and where the secret of their existence could be preserved even if the enemy recovered fragments from destroyed aircraft. That moment arrived on the morning of January 5th, 1943. Helena had departed from Guadalcanal before dawn on January 5th, after participating in a bombardment of Japanese positions at Munda on New Georgia Island. The cruiser-destroyer task force was returning to base when the 4 Vals appeared seemingly from nowhere, a coordinated dive-bombing attack that caught the formation partially by surprise. One bomber scored a hit on the New Zealand cruiser Achilles, damaging but not sinking her. The other 3 completed their dives and were climbing away, gaining altitude and speed for their return flight to their base at Rabaul. Standard procedure called for saturation barrage fire, throwing as many shells as possible into the sky at various altitudes, creating a steel curtain that the enemy aircraft might fly through. The probability of hitting anything was low, but the volume of fire sometimes got lucky, and at minimum it made enemy pilots nervous and disrupted their attack runs. Helena's gun crews had conducted this type of barrage fire dozens of times over the previous months. It rarely accomplished much beyond consuming ammunition, but this morning, Lieutenant Commander Cochrane had different orders. Use the special ammunition, fire-controlled salvos at specific targets. Let the shells do their work. The first salvo of 3 rounds arced upward toward the nearest retreating Val. The shells passed perhaps 50 yards from the aircraft close, but not close enough by conventional standards. No explosions. The crew felt a moment of doubt. Were these special shell duds? The second salvo corrected slightly, tracking Val's trajectory more accurately. Again, no visible effect. The bomber continued climbing, now perhaps 4,000 yards distant. Cochrane ordered the third salvo. His gun crews loaded, aimed, fired. 6 seconds after leaving the barrel, somewhere in that empty air near the climbing bomber, all 3 shells detonated simultaneously. The destruction was immediate and total. The Val's wings shredded under the impact of steel fragments traveling at thousands of feet per second. The bomber's control surfaces disintegrated. Fire erupted from its fuel tanks as shrapnel punctured them, and ignition sources were plentiful. The aircraft rolled, inverted, and began its death spiral, pieces continuing to tear away as it fell. By the time it hit the water, barely recognizable as an airplane. The gun crew stood in stunned silence for perhaps 3 seconds before the significance registered. Then, pandemonium. Shouting, celebration, men pounding each other on the back. They'd just shot down an enemy aircraft without hitting it. The shells had exploded themselves when they got close enough. Whatever these special rounds contained, they worked exactly as advertised. Commander Parsons, observing from nearby, immediately drafted his combat report. The VT fuse had achieved its first confirmed kill under actual battle conditions. The technology worked. The Navy had just acquired a weapon that would fundamentally alter the balance of power in the Pacific Naval War. Word spread quickly through the fleet, though the details remained carefully classified. Other ships reported similar successes over the following weeks. In February, Admiral Halsey's task forces came under repeated night attacks by Mitsubishi G-4M Betty bombers, attempting to torpedo American ships in the Solomons. Conventional anti-aircraft fire struggled to engage effectively in darkness. Time fuses required accurate range and altitude data that radar could provide, but with limited precision. The Bettys had been achieving disturbing success rates in these night attacks. With VT fuses, darkness became irrelevant. Radar could track the incoming bombers. Gun directors could point the guns in the correct general direction. The shells themselves handled the precision targeting. Night after night, flaming Japanese bombers fell into the sea, their crews never understanding how American gunfire had become so accurate after dark. One attack in late February saw 12 Bettys attempt a coordinated strike. 5 were shot down, the convoy they'd targeted remained undamaged, and Admiral Halsey's staff began requesting massive increases in VT fuse allocations. The statistical evidence accumulated rapidly. During 1943, Navy ships fired 9,128 rounds of 5-inch VT ammunition in combat. Those rounds achieved 61 confirmed aircraft kills. That translated to 155 rounds per kill, a number that seemed almost impossible compared to previous performance. Conventional time-fused 5-inch shells required an average of 508 rounds per kill during the same period. The VT fuse was more than 3 times as effective per round fired. But those numbers told only part of the story. The real revolution was in what the VT fuse enabled tactically. Previously, ships under air attack had to wait until enemy aircraft closed to relatively short range before anti-aircraft fire became even theoretically effective. Open fire too early with time fuzzes, and you simply wasted ammunition shooting at empty sky while the enemy maneuvered. The VT fuse eliminated that restriction. Gunners could open fire the moment the target came within maximum range, approximately 10,000 yards for 5-inch guns, and every shell fired had a meaningful probability of causing damage if it passed anywhere near the target. This created a defensive envelope that enemy aircraft could not easily penetrate. Where previously a bomber formation might accept some losses while pushing through to reach bombing range, VT-fused defensive fire made that approach suicidal. Aircraft began taking damage or being destroyed at ranges where the bombers couldn't even engage their targets. Attack runs that previously succeeded through determination and accepting casualties now failed before they could begin. Japanese aircrew who survived these encounters reported confusing and demoralizing experiences. Anti-aircraft fire that seemed to explode everywhere around them without warning. Shells that detonated when they shouldn't, at ranges and altitudes where conventional barrage fire would have been harmless. Bombers losing wingmen to explosions that appeared to come from near misses. The psychological impact compounded the physical casualties. Pilots who'd previously considered themselves reasonably safe at certain altitudes or ranges discovered that nowhere in the sky near American ships offered safety anymore. Japanese naval intelligence attempted to understand what had changed. Initial theories focused on improved American training and better fire control radars. Some analysts suggested the Americans had developed new types of explosive that had larger fragment patterns or more powerful blast effects. A few investigators came tantalizingly close to the truth, hypothesizing some kind of advanced fuse mechanism, but without access to intact examples they couldn't confirm the speculation, and the idea of miniaturizing radar into an artillery shell seemed so impractical that most dismissed it as impossible. The secrecy proved remarkably effective. Despite hundreds of VT-fused shells being fired in combat through 1943 and into 1944, the Japanese never captured an intact example and never developed a clear understanding of how the technology worked. This intelligence failure had profound consequences. Unable to develop countermeasures, unable to even understand what they were facing, Japanese forces simply had to accept that American anti-aircraft capabilities had improved dramatically for unknown reasons. Production accelerated through 1943 as the Navy realized the magnitude of what they'd achieved. The factories that had been producing 500 fuses daily at the end of 1942 expanded to 40,000 fuses daily by late 1943. By war's end, production peaked at 70,000 fuses per day. Manufacturing involved over 110 factories across 87 different companies, employing tens of thousands of workers, most of whom never knew what they were building. The cost fell from $732 per fuse in 1942 to $18 by 1945, as manufacturing efficiency improved and economies of scale took effect. By 1944, The majority of 5-inch anti-aircraft ammunition in the Pacific Fleet carried VT fuses. The Navy had moved from cautious experimental deployment to wholesale adoption. Every carrier task force, every cruiser, every destroyer capable of carrying 5-inch guns received ample stocks of VT ammunition. The doctrine had evolved from considering these special rounds to be used sparingly for critical situations, to treating them as standard anti-aircraft ammunition. The statistics from 1944 showed both the increased deployment and some interesting complexity. Ships fired 32,826 VT-fused rounds and achieved fewer kills per round than the previous year, roughly 421 rounds per kill. This apparent reduction in efficiency initially concerned some analysts until they examined the tactical context. Doctrine had shifted to emphasize early engagement, opening fire at maximum range even when hit probability was low, using the weight of fire to disrupt and damage enemy formations long before they reached effective attack range. The goal wasn't necessarily to shoot down every enemy aircraft with minimum ammunition expenditure. The goal was to prevent those aircraft from successfully attacking American ships. If you could damage a bomber at 8,000 yards, forcing it to abort its attack run or drop its weapons early, that was mission success, even if you didn't achieve a kill. The apparently reduced efficiency actually represented improved tactical employment, trading ammunition for guaranteed mission success. But 1945 would prove the VT fuse's greatest test and most decisive contribution. The Japanese, faced with collapsing defensive perimeters, dwindling numbers of trained pilots, and the increasingly obvious futility of conventional attack tactics against American naval forces, embraced the Kamikaze Special Attack Corps with desperate determination. If your aircraft were going to be shot down anyway approaching American ships, if your chances of survival executing a conventional attack and escaping were effectively zero, then accepting certain death while guaranteeing a hit made terrible pragmatic sense. The kamikaze attacks presented a unique challenge. Conventional bombing and torpedo runs gave anti-aircraft gunners extended engagement opportunities as the enemy aircraft maneuvered into attack position. Kamikazes came straight in at maximum speed, minimizing the time available for engagement. They couldn't be discouraged or forced to break off. The pilot had already committed to death. Damage that would cause a conventional attacker to retreat was irrelevant to a kamikaze. You had to destroy the aircraft completely, and you had to do it before it reached your ship. VT fuses proved devastatingly effective against kamikaze attacks despite their intensity. The statistics from October 1944 through January 1945 showed 5-inch guns firing VT ammunition, requiring 310 rounds per aircraft destroyed against kamikazes, compared to 1,162 rounds for conventional time-fused ammunition. That 3-to-1 advantage meant the difference between ships surviving and ships sinking. The Battle of Okinawa, in spring 1945, saw the heaviest kamikaze attacks of the war. Between March 18th and August 15th, the Japanese launched over 1,500 kamikaze attacks against the American fleet stationed off Okinawa. The casualty figures were brutal on both sides. The Navy lost 21 ships sunk and 66 damaged, suffering thousands of casualties. But the Japanese lost virtually all of their attacking aircraft and the irreplaceable pilots who flew them. In one particularly intense action on May 11, 1945, the destroyers USS Hadley and USS Evans, along with 4 landing craft support ships, faced a coordinated attack by 156 kamikaze aircraft over 90 minutes. The small formation found itself under assault from waves of suicide aircraft, diving from multiple directions simultaneously. This represented every anti-aircraft gunner's nightmare scenario: too many targets, too little time, insufficient firepower to engage everything. But Hadley and Evans carried full loads of VT-fused ammunition. Their 5-inch guns, firing under the direction of radar-controlled gun directors and equipped with proximity fuses that guaranteed effectiveness against any target they could point at, systematically destroyed the attacking aircraft. The engagement report later tallied the results. Hadley shot down 12 enemy planes before being hit by kamikazes that broke through the defensive fire. Evans accounted for 23 confirmed kills before she too took hits. The supporting vessels contributed additional kills. Of the 156 attacking aircraft, the tiny formation destroyed approximately 51/3 of the attackers before kamikaze hits forced both destroyers to retire from the battle. Admiral William Halsey, after reviewing the action reports, called the VT fuse indispensable to the ship's survival. Without proximity fuses, facing that volume of simultaneous attacks, the formation would likely have been annihilated. With VT fuses, they'd inflicted devastating losses on the attackers, while surviving with damage that, though severe, proved repairable. Nearly 2/3 of all VT fuses expended during the entire war were fired during just 7.5 months in 1945, primarily against kamikaze attacks. That statistic captures both the intensity of the final Pacific campaign and the absolute dependence American forces had developed on this technology. The proximity fuse wasn't an experimental weapon anymore, or a specialized tool for specific situations. It had become the foundation of naval air defense, the technology that made American ships survivable in an environment where hundreds of Japanese pilots were willingly flying themselves to death to sink those ships. The VT fuse found applications beyond naval anti-aircraft defense, though these came later due to the initial security restrictions. The British employed proximity fuses extensively against German Von flying bombs attacking London in mid-1944. The cruise missiles presented perfect targets unmanned, following ballistic trajectories, small and fast. Conventional anti-aircraft fire struggled to engage them effectively. When VT-fused ammunition became available, the kill rate soared from 17% in June to 74% by late August. During one particularly effective day, of 104 V1s launched toward London, 68 fell to proximity-fused anti-aircraft fire. The fuses saved London from months of additional bombardment. General Eisenhower finally received permission to use VT fuses in ground artillery during the Battle of the Bulge in December 1944. The tactical restriction against land use was lifted once Allied commanders determined that the war in Europe was too far advanced for the Germans to develop effective countermeasures, even if they captured intact examples. Artillery shells fused with VT proximity detonators exploding in airbursts above German infantry formations proved devastating. General Patton credited the funny fuse with saving Liège and called it one of the war's decisive weapons. Post-war interrogations of German and Japanese military leadership revealed the extent of their ignorance about proximity fuses. German officers knew that Allied anti-aircraft fire and artillery had become dramatically more effective, but had attributed it to improved fire control systems, better training, and superior logistics, allowing more ammunition expenditure. Several German research programs had explored proximity fuse concepts, but these had been cancelled in 1940 due to directives requiring any development project to be completable within 6 months to support immediate war needs. The long-term research required to solve the miniaturization and ruggedization challenges was abandoned. Japanese military investigators, even after the war ended and American forces explained the VT fuse technology, expressed disbelief that vacuum tubes could survive artillery launch. Their own research had concluded this was impossible, and they'd never seriously pursued development beyond preliminary studies. Learning that the Americans had achieved what Japanese scientists considered impossible helped explain the mystery of why their aircraft had been dying in such numbers to anti-aircraft fire that seemed impossibly accurate. The program's final statistics captured its scope and impact. Over 22 million VT fuses were produced during the war at a total cost exceeding $1 billion 1940s, roughly equivalent to $15 billion today. The project's priority and funding rivaled the Manhattan Project's. More than 100 factories and 2,000 subcontractors participated in manufacturing components and assemblies. At its peak, the VT fuse program employed tens of thousands of workers, consumed significant portions of America's electronics manufacturing capacity, and represented one of the first large-scale applications of printed circuit boards in mass production. The effectiveness ratios bore out the investment's value. Secretary of the Navy James Forrestal stated that the proximity fuse helped blaze the trail to Japan. Admiral Arleigh Burke, who commanded destroyers in the Solomons campaign and later served as Chief of Staff to Admiral Mitcher's Fast Carrier Task Force, said the fuses knocked down enemy planes by the dozens, and that without them, our ship losses and casualties would have been enormously larger. Vannevar Bush, director of the Office of Scientific Research and Development, credited the proximity fuse with 3 decisive effects: defeating kamikaze attacks, neutralizing Vone attacks on London, and revolutionizing field artillery effectiveness. Some historians argue the proximity fuse's importance exceeded even these assessments. Without it, the carrier task forces that projected American power across the Pacific might have suffered unsustainable losses to conventional air attack long before kamikaze tactics emerged. The island-hopping campaign that brought American forces to Japan's doorstep relied on carrier air power for support and protection. Ships that couldn't defend themselves effectively against air attack couldn't support the amphibious operations that seized islands progressively closer to the Japanese home islands. The kamikaze campaign alone, absent effective countermeasures, might have forced fundamental strategic recalculation. At Okinawa, even with VT fuses providing dramatically improved defensive capabilities, the Navy suffered over 9,000 casualties and lost significant numbers of ships. Without proximity fuses, facing the same intensity of attack with conventional defensive armament, the casualty rates would have been catastrophic, potentially unsustainable politically, and certainly unsustainable operationally. The invasion of Japan's home islands, planned for late 1945 before the atomic bombs ended the war, would have required fleet operations in close proximity to thousands of potentially kamikaze-capable aircraft. Under those circumstances, VT fuses might have made the difference between a viable operation and a strategic impossibility. The technology's legacy extended long beyond World War II's end. Every modern guided missile essentially implements the proximity fuse, principle detecting target proximity and detonating at optimal range to maximize damage. The Patriot surface-to-air missiles, the Standard missiles defending American warships, the AMRAAM air-to-air missiles, all employ sophisticated proximity, sensing far more advanced than the simple radio circuits of the Mark 32 fuse, but implementing the same fundamental concept that Section T's engineers proved in 1942. The development process itself became a template for future military research programs. The combination of theoretical research, engineering development, rapid prototyping, continuous testing and refinement, and crash production represented a new model for translating scientific concepts into fieldable military hardware under the extreme time pressure of wartime emergency. The Manhattan Project followed similar patterns. So did radar development. So did proximity fuse development. These 3 programs collectively established the framework for modern military research and development, the recognition that sufficient resources, proper organization, and talented personnel could solve seemingly impossible technical challenges in timeframes that peacetime development schedules would consider fantasy. The VT fuse also demonstrated the decisive advantage that technological sophistication could provide, even against determined, courageous, well-trained opponents. Japanese naval aviators in 1942 and 1943 were among the world's most skilled pilots, flying excellent aircraft with effective weapons. Their tactics were sound, their determination was absolute. But they were flying into a defensive environment that had suddenly shifted from marginally effective to lethally precise, and they had no technological counter to that shift. Courage and skill couldn't compensate for physics. Training couldn't overcome the mathematics of a weapon system that turned every shell into a proximity-triggered fragmentation warhead. This lesson that technological advantage can prove decisive, independent of traditional military factors, shaped post-war strategic thinking throughout the Cold War and beyond. The side with better sensors, better guidance systems, better computing, better integration of these technologies into weapons platforms gained advantages that numerical superiority or tactical brilliance couldn't easily overcome. Modern warfare increasingly became a contest of engineering and scientific capability as much as conventional military power. The human cost of the VT Fuse program, measured not in casualties but in lives saved, remains incalculable but substantial. Every aircraft shot down before reaching its target represented bombs or torpedoes not delivered, attacks not completed, ships not damaged or sunk, sailors not killed or wounded. Every transport that reached Guadalcanal safely because attacking bombers were destroyed before dropping their weapons represented hundreds of Marines landed, supplied, and supported. Every carrier that survived to launch strikes because its defensive envelope deterred or destroyed. Attackers represented thousands of sorties flown and targets destroyed. Admiral Burke's assessment that VT fuses prevented enormously larger losses in the fast carrier task forces represents conservative understatement when examined against the casualty statistics from actions where proximity fuses proved decisive. The difference between a kamikaze attack succeeding or failing meant the difference between a ship continuing operations or withdrawing for repairs, between casualties in dozens or casualties in hundreds, between missions accomplished or missions aborted. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe. The morning of January 5, 1943, when Lieutenant Commander Cochrane watched Val disintegrate in mid-air off Guadalcanal, marked a turning point that few recognized at the time but which proved as significant as any tactical or strategic innovation of the Pacific War. The VT fuse didn't win the war alone, no single technology did, but it enabled the projection of naval power under conditions that might otherwise have proven prohibitively costly. It demonstrated American industrial and scientific capability operating at maximum effectiveness, and it exemplified the principle that impossible problems sometimes yield to determined engineering, adequate resources, and refusal to accept that impossible means unachievable. The Japanese never expected 5-inch guns to achieve 90% improvement in effectiveness. They never imagined that miniaturized radar could fit inside an artillery shell and survive firing. They never anticipated that American forces would solve in 2 years what British researchers had concluded couldn't be solved during the current war. That failure of imagination, that gap between what seemed possible and what actually was possible, cost them thousands of aircraft, irreplaceable pilots, and ultimately contributed to their defeat in the Pacific. The future belonged to the side that made impossible things real, and in the contest to miniaturize radar into artillery shells, the Americans won decisively. The proximity fuse represented something unprecedented in military history, a weapon that worked by making shells intelligent. For thousands of years, projectiles had been fundamentally dumb. The VT fuse changed that equation fundamentally, giving each shell the ability to detect its environment and decide when to detonate. Years later, Lieutenant Commander Francis "Red" Cochrane would reflect on that January morning off Guadalcanal with a profound sense of history. He hadn't just commanded a gun battery that day, he'd witnessed the birth of smart weapons technology that would transform warfare forever. The quiet, unassuming officer who had stood on Helena's deck watching pieces of that Val bomber rain down into the Solomon Sea would eventually rise to the rank of Rear Admiral, consulted by generations of weapons designers seeking to build upon the foundation laid by those first proximity fuses. When the war ended, Cochrane was among the few officers permitted to fully understand what had happened that day. The 22 million proximity fuses produced during the war had saved countless American lives, neutralized the kamikaze threat, and demonstrated that American ingenuity could make the impossible possible. What began with that single Val bomber would evolve into the sophisticated guided weapons that define modern warfare, the AIM-120 AMRAAM missile, the standard SM-2, the Patriot PAC-3, all tracing their lineage to Dr. Tuve's determination to make artillery shells smart enough to know when to explode. The technical achievement was extraordinary. The tactical impact was decisive. But as Cochrane would later tell naval cadets at Annapolis, the human achievement was even more remarkable. Thousands of engineers, scientists, and workers who never knew exactly what they were building had collectively changed the course of history. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.